Oh, yeah. Sweet home Alabama. Yeah. Oh yeah, I forgot I'm making a video. I should turn this off. Oops. Okay. Back to what it is we're supposed to be doing, and that is finishing up a lab where we determine the acceleration due to gravity as located here at our little high school. All right. This strip of wax paper we found by using what was known as a, can we write it down somewhere? A Behr, B-E-H. Oh, I'm not sure I should write on this with a pen, but a Behr accelerometer. Accelerometer. Can you read wax paper writing via a camera? I don't know. But anyway, what that accelerometer did was it had a freely falling plummet, and every 60th of a second, probably messed up my marker, every 1/60th of a second it created a spark on this paper as the plummet fell. Now what we've done is we've measured every other spark. So we've actually got a time difference of 1/30th of a second here. So all we're going to do in this lab, we laid a tape measure down beside this tape that we put marks. We put a mark through each dot. So there's a dot, there's a dot, there's a dot. So every other dot we put a mark through. We laid a tape down across it. We laid a tape across it. And then we recorded the position of every other dot across here. And then we also know that the time between every other dot is 1/30th of a second. And so hopefully what we'll find, we'll be able to find a velocity for each single path along here. They keep getting farther and farther apart as we get towards the bottom. And that's because of the acceleration of that plummet. Anyway, we should be able to find a velocity for this section, this section, this section, this section. And if we continue to find all those velocities, then we should be able to find the rate of change in velocity, which that's all acceleration is a rate of change in velocity. So here's a sample of some data that I took from in the lab off one of these. Now the group I did laid their tape down specifically and made their first line 0. I actually don't like doing that. I'd rather randomly lay the tape down and then get measurements post that. But anyway, this is what I'm stuck with, so I'm going to go with it. So the first thing I need to do is determine the distance. I need to determine the distance between each one of these positions. Well, my first position, there's not going to be anything there. But anyway, so what is my distance between my first two positions? Well, the distance between 0 and 5, that's 5.0, so that's not too hard. Then the distance between 11.2 and 5, so I'm going to take this difference, 11.2 and 5, that's going to be 6.2. And then 18.4 minus 11.2, that's going to be 7.2. 27 minus 18.4. Sorry, this is the less than exciting part of the video, me subtracting numbers. Feel free to fast forward to the end. Here, I'll pretend 9.5, this times this times this, 0.6, 11.6, 12.8. Holy cow, look at how fast I can subtract. It's almost like I've done this on another sheet of paper already to speed up the video. Okay, so here's my distance between all my positions. You should notice the distance increasing as I go down this list. It should. The plummet was traveling faster as it fell towards the earth. Now, I'm only going to write one generic time over here because the time between every one of these was 1/30th of a second. The time between each one of these distances was a displacement that occurred over 1/30th of a second. And if you're trying to figure out why the 1/30th, again, the spark generator was set to a 60th of a second, but I actually tuned it back to, we used every other dot, so that brought us to a 30th. So now look at what we know. We know at this time, we know distance and we know time. Well, distance divided by time will give us an average velocity. And if you have trouble, that is my V, by the way, sloppy as it may look. But anyway, that is my average velocity. So all I got to do is divide each one of these numbers by 30. Well, 5 divided by 1/30. Well, dividing by 1/30 is the same as multiplying by 30. So that's going to be 5 times 30. So this one will be 150. And I'll save you the suspense. 186, 216. Again, all I'm doing is multiplying each of these numbers by 30 to get this velocity. 216, 256, and you can see how I'm speeding up. 285, 318, 348, 384, 417, and 444. Congratulations, we have a complete data table at this time. Okay, now what I'm going to do with this data now is probably the part most people have problems with. I'm going to make a graph at this point. Hopefully it will be a good graph, a graph we can be proud of. So I'm not going to move this data off too far. I am going to need it again. But let's start a graph for a science class. And a lot of people, oh no, I'm moving my camera, which may throw me into a state of panic. But oh well. I'm going to do my best to write on here. It's going to be hard to make my writing stand out on this graph. But any graph or any lab report, you should have a name and date up in the corner of it. So we're going to put a name and a date up here in the corner. All right. So I'll put my name and date here. Also, I now need a title to go back here. And I'm going to call this graph acceleration. Acceleration due to gravity. Now, you don't actually have to write this big on your graph. It's just that I want to make sure you can read it via YouTube or the internet. So, now as we come back through, I am going to do one more thing up here. Every time you ever make a graph, you should include at the top what it's a graph of. It should be something versus something. You should say what this is going to be, a graph of the y versus the x. You should have a statement up here. And if you have a big report with a bunch of graphs, this helps you know which graph you're talking about. This is part of the title. This is really the title to this graph. My graph is going to be a graph of velocity, average velocity in centimeters per second versus time in seconds. So that's what my axes of this graph are going to be. So my left axis over here is going to be velocity or average velocity in centimeters per second. Again, I'm writing huge because of this little video thing here. The bottom, I'm going to have time in seconds. Now, one thing that honestly I should have already done, and I haven't done yet, I should really have already have made my axes on this graph paper. You should never, ever make a graph using the edge of the paper as an axis. So what I'm going to do is take my graph, I'm going to lay a ruler. I'm going to pick, this is 10 division per inch paper. I'm going to lay my ruler down here. You shouldn't use a Sharpie this big. It's just, this is all I've got, kind of. And I've about missed my axis a little bit here. It's the problem with using a big, huge Sharpie. Now to go down to the bottom, and I'll do the same thing. I'm going up the first bold line from the top and the bottom. Oh, I did a great job there. So you should make a set of axes for this graph. So now we've got axes for our graph. We've got our title, our name, date. I mean, we've come a long way here. This is going to be a good-looking graph. I can already tell. Well, we need to lay out a scale. Well, my scale going left to right is going to be easy. All I'm going to do each time across the right is I'm going to go up 1/30th every single time. So that would be a 30th. This would be 2/30ths, 3/30ths. And yes, I know that reduces to 1/10. Please don't remind me of that. I'm doing this for ease of graphing. 4/30ths, 5/30ths. You should be writing much smaller. 6/30ths, 7/30ths. Where are we? 8/30ths, 9/30ths, 10/30ths. Yes, I know it's a third. 11/30ths. 12/30ths. And if I went to the edge of the paper, it'd be my 13/30ths mark by the time I get to there. But now, what about our axis going up? This is actually a hard part people struggle with in science sometimes. You need to use as much of your graph paper as possible. And you want your axes to kind of go with your data. My data starts at 150 and finishes at 444. Now, you could come in here and just say, okay, I'm going to make this 100, 200, 300, 400. Well, the problem is, at that point, I would be wasting the entire rest of this graph paper. So I want to try and best use 100 to 444. So I'm going to back up here and figure out what would be the best. Well, if I went by 25s, that would be 25, so 5 lines up, 25, 50, 75, 100. So there's 100. And then 5 more lines up, 125, 150, 175. And of course, 200 is slapped right in the way. 200 right here, 225, 250, 275. So there's 300. Again, it would look much neater if I was doing this with a smaller Sharpie. 325, 350, 370. I'm not even on the paper. So here, I'll move it down. 400. And that gets me 425, 450, 475. So I'm 475 to the top, which is fine because my biggest number is 444. I just made a spectacular graph, other than how ugly it is. Now, I do want to do one thing. I do want to talk about my scale a little bit. This is 100, so that's 25. That means each line I go up on this is going up 5. So I need to know that over here. Now, vice versa, this way, 5 lines makes a 30th. That means left to right, each of these lines is 1/150th. And that may come in handy for me to know later, that each little line across this paper is 1/150th of a second is what this is. And just so you don't think, man, this guy makes really ugly graphs. This is what mine looks like when I actually did it, you know, trying to be really neat with it. So I've actually got much neater here. I even reduced all my fractions. I did accidentally put meters per second instead of centimeters per second. Look at how much neater my title is, my name and my date. This is what it should look like. This should be much better, used with a smaller, finer tip Sharpie. And so, anyway, but for the sake of this video, I'm going to go back to ugly grapho here. So, what I want to do is I want to graph this data now. Well, my data, and I'm going to do it like this. I'm going to slide this over, see if I can get room for my data in my graph. I doubt it. My first data point is 150. Now, this is my y-axis. So I want to go up 150 on my y and over a 30th of a second. So here's a 30th. So I want to go up 150. Well, there's 100, 125, and 150. So that one's really easy for me. And I'm going to put a data point here. Well, my next data point for me is 186. So again, I'm going to go over another 30th and go up to 186. Well, let's see. That would be 175, 180, 185. So 186 would be just above that. And now I'm going to try and speed this up. 216. So there's 200, 205, that's 210, 215. I'm going up 5, so 216 would be right here. And I shall now keep going. 256 would be here. 285, well, let's see. There's 275, so 285. Oh, I'm loving this. 318 would be here. Oh, look at how neat my graph is looking. Won't everyone be jealous of me? 348, 384 would be, this could be the greatest graph in the history of graphitude. 417, and then I'm going to end up in my title. 444 is going to end up, right up here. After you've laid your data points on, somebody's going to say, what happens if we got one that's way off? Well, if you got one that's way down here, just put an X across that one and ignore it when you make your graph. Now, this graph is beautiful. Most of the time when you make a graph, it is not going to end up quite so perfect. Like, look at this line. I can lay a ruler on here and almost, draw that ruler. I can almost hit every single dot on this line. The better question would be this. What happens when you go to do a graph and your dots look like this? What happens when your dots, well, this is where you make what's known as a trend line. And what you're going to do is this. You're going to take your ruler. Now, if there's one that's like way off, you're going to assume that one, something's wrong. So you're going to put an X, not quite so large, but put an X on it. Lay your ruler across here. Now, when you lay a ruler on the graph, you need to lay that ruler all the way across the paper. And when you mark the graph, you need to put the mark from one end to the other. What you're going to do is try and get this ruler centered to best fit the data. This is known as a best fit line that I'm drawing. So I'm going to lay this ruler on, try and see if I can't get a best fit line. And I'm going to now draw a line through that data. Now, does it necessarily hit any of the points? No, it doesn't have to hit any of the points. But I want it to run through the points. Hey, I hit this one. That's pretty good. It didn't hit the origin. You don't have to always hit the origin of a graph. I think that's something you get taught somewhere that's not right. But anyway, I'm going to do the same thing now with this data. I'm going to take a ruler. I'm going to lay it on here. And I'm going to be crazy. I'm going to draw it through the title. I don't care. I want this line to go all the way through it. Now, once again, the difference. You do not need to be using a fat-tipped Sharpie for this. You need a pencil, 0.5 millimeter. It needs to be precise and clean. Center this target up, and now draw a line all the way. Look at this line. Look at this. I drew it into the white. I'm not scared. I drew it off the graph because I'm not scared. And look, I hit almost every line. This is a perfect looking graph. Now I want to pick some data points. Pick some graph points. I want a slope off this graph. So, see if I can find the slope. And I know this is going to be a really long video. Just bear with me here. For my slope, what I'm looking for is this. I want to find, if you've watched other videos of mine, you've seen this. If this is a set of crosshairs on the graph, I want to find where the line that I just drew, makes a perfect, hopefully more perfect than that. Let's try again. That's not what I'm looking for. I'm wanting to find at least two, and surely over this whole line I can find two. I want to find the spot where it looks even better than that. That's still not good enough, but, for sake of time, I'm going to try. I want to find spots where my line makes a dead intersection on this graph paper. And I promise, and this is why my line's too fat. I need a smaller line. But I can find 2 points. And when I just found one right here. And when I find that point, I'm going to bold it up a little and I'm going to put a circle around it. And I'm going to look for another one somewhere up in here. Oh, goodness, right here. Look at you. Aren't you pretty? So now I've got 2 points. And I need to define those points. I want to say where those points are. So this is going to be my x1, y1. And I could call it t1, v1 instead of x and y, since I labeled it v and t, but that's not important. I'm going to come up here and I'm going to do the same thing. I'm going to call this one up here x2 and y2. And wow, I kind of uglified that a little bit. I need to write down where these locations are. So I need to know how far over X am I. Well, let's see. 1, 2, 3, 4, 5, 6, 7. I am 7. Each one of these lines is 1/150th. So I come over 7 1/50ths. Comma, I went up 100, 125, 150, and let's see, each line's 5, so there's 150, 55, 60, 65. So I'm up 165. This location, ooh, we're going to have to do some counting here. 10, 20, 25, 30, looks like I am 33 lines over. So each line is 1/150th, so I am over 33 1/50ths. Comma, I am up, well, let's see, there's 300, 325, so that makes that 330, 335. Now, this calculation, whenever you do a slope, you should do a slope calculation on the graph. So you should come right here, slope equals, and work this slope out. Now, I'm thinking about doing on another sheet of paper so it's not be quite so messy with it. So let's see what I can do. Slope, again, you should do it on your graph. Slope equals rise over run, y2 minus y1 over x2 minus x1. So in my case, I've got 335 minus 165 on top. 335 minus 165, draw my line. Bottom, I've got 33 1/50ths minus 7 1/50ths. And now, I can't wait to see what I've got here. I'm going to use my fancy calculator functions here. 335 minus 165. Then I'm going to do 33 over 150 minus 7 over 150 is 112,750 over 13. Let's change that to decimal. Holy cow! Look at this. 980.76 repeating numbers. Truth is, I'm going to go ahead and round it off to just 980 meters per second square. So I have just found acceleration, or gravity, is 980, which means, check out my percent error calculation. E minus A over A, absolute values, times 100. Do I even have to go there? You knew it was going to be perfect, though. 980 minus 980 actual over 980. I had a 0% error in this lab. Now, again, this calculation should be on this graph. I should see 980 meters per second square. Matter of fact, I also want to know a second thing. I want to know this intercept over here, which for me, I'm intercept 105, 110, 115. I've got an intercept of 115 on this. And I want to see if you can figure out what the intercept is. Well, let's write the equation for this line. The equation for line is y equals, I remember when I first went to college, every lab, they wanted you to do this equation for line. Y equals mx plus b. Well, in this case, your y is, let's see if we can get this. Your y is a velocity. M is 980, X is time, and then your intercept is, for me, 115. Look at what you've got. V, that's an acceleration and a time. That's a V. V equals VO plus AT. 980. Have you figured out what 115 is? It's velocity initial. Because think about it. The plummet was already moving when you started recording your data. So you had an initial velocity of 115 centimeters per second when you first started recording data. All right. Again, in your conclusion, you should make sure and say gravity. You should have sources of error. You should have all these things. But anyway, I hope this helps. 25 minutes in, I feel like I need to draw a gigantic smiley face because you get an A for effort for listening to this whole video. Oh, I should quit physics and I should take up art classes. It's amazing.